Hello, MEGN 200. This is Dr. Wheeler here, coming to you from the spare bedroom studio today. Hope you're all enjoying your snow day. Anyhow, I wanted to make a video to show you some of the key points on the homework assignment that we were assigning this week. Since next week we are going into a MATLAB project and we don't want to fall behind in that class, I'm going to make a video. You can watch this on your own time to help you get the homework assignment for this week done. This week's homework assignment focuses on writing custom MATLAB functions and doing some advanced data visualization. So we'll talk about what the goals of this particular project are first. So what you should be doing on worksheet 3 is you'll be learning how to write your own MATLAB functions. So far we've only used predetermined MATLAB functions that are built into MATLAB when you download it. You can actually write your own code as a function, and that allows you to make some more complex coding projects. So we'll talk about how you can set that up. We'll also use MATLAB's plotting functions to create some more complex figures than what we've done so far. And then finally, you'll also learn how to use the animated line function in MATLAB to create an animated plot if you want to have a little video showing your data popping up on the screen. All right, so let's jump into talking about functions. All right, so functions, as you might remember from your intro to computer science classes, they allow code to be modular. So we can write a section of code that we might want to reuse more than once in a function, and we can call that function multiple times in other parts of the program. So instead of having to copy and paste the same code over and over again everywhere where we need it in our project, we can just write the function once and then just call the function in various situations. Okay, so this helps you keep your code well organized, especially in larger projects where you have multiple different parts of the code that need to interact with one another. It's helpful to write those as functions so that you can just easily reaccess that code multiple times. All right, the syntax in MATLAB for functions is pretty important to let MATLAB know that you're trying to make a function rather than just a normal script. So functions in MATLAB always start with the function keyword. So we've got that in the image there to the right on your screen. We start off the .m file with this function keyword that tells MATLAB, hey, we're declaring a function in this particular M file. Key thing with saving that .m file, the .m file name that you save it as has to be exactly the same as the name of the function that you're defining in that .m file. So watch out for that. If you get an error, that can be a common thing that you run into when you try and save the file. It'll let you know, hey, the function name and the file name don't match. So just make sure that they are exactly the same. That's case sensitive also. Okay, and then we declare the function with the function keyword. Then the syntax is we have our output variable, and we set that equal to the function name with then the arguments to the function going in parentheses. Okay, so the function is going to work exactly the same as all the MATLAB built-in functions where you put the function argument in the parentheses and then it spits out some sort of output. We're doing the exact same thing here, but we just have to declare that in the function M file. Okay, and then in between the function keyword and the end keyword that closes off the function, we put our code that takes the input arguments, manipulates them however we want to manipulate them, and then defines the output variable, which gets returned by the function. All right, so in our code here, we've called our output variable output. That is the value that's going to be returned by the function. So when we call this code, it's going to take our input argument in the parentheses, do something to the input argument, and then it returns the value that we put into output. So when we're writing our code, we write whatever we need to do with the arguments. We can manipulate that however we would want to, just like if we were writing a script file, but then we have to define this output variable. Say output equals somewhere inside of the function, and then whatever value is stored in output when the function gets down to the end keyword gets returned by the function when we call it in MATLAB. All right, and just on those input arguments, you can use whatever sort of data type that you want in there. So we can input scalars, we can input arrays, you can input a cell array, you could do structures, whatever sort of data that you have in MATLAB, you can pass it into a function, and then same thing with the function output. That can be any sort of data type that we want, and we don't have to worry about declaring that in the function itself. MATLAB handles all of that behind the scenes. So unlike C or sometimes in Python, you don't have to say what sort of data type you're working with. All right. So if you can have multiple inputs and outputs to a function, right? So if we wanted to do that, when you're defining multiple function outputs, we use the square bracket notation. Just if we list out our different output variables inside of the square brackets with separated by commas, and then you're also allowed to have multiple arguments, input arguments into the function. So those are just separated with commas, just like we do in the built-in MATLAB functions. All right, so we're going to have an example today where we'll use some functions that have been downloaded from the MATLAB Central, which is just a big repository of user-created functions and scripts. So you can go oftentimes to find a custom function that does something that you're interested in that doesn't exist in the MATLAB-based installation. Chances are somebody's written a code to do that, and you can download and use their functions. We're going to be downloading a couple of codes to create the Reuleaux triangle, which you might know as the Minds logo. So that geometric shape, we're going to try generating that in MATLAB and then plotting it, making it look really nice with some of the more advanced plotting functions. Okay, so we'll be downloading a couple of codes that help us make that. We'll also be writing a custom function that creates circles, and we will show how you can generate this Reuleaux triangle by plotting 3 circles that overlap one another. The space where they overlap is actually the Reuleaux triangle. Okay, so then we'll write a main script that calls all the functions and then formats the plots to make them look nice. So we'll have function that generates circles. We'll have 2 functions that generate a Reuleaux triangle that we can plot, and then we'll call those functions inside of a main script to actually create the plots. So just give you an overarching view of what this program ends up looking like. We have a main script file that calls the functions that we define. Okay, so the main script file is going to call the functions, and then it creates the plots. We'll be creating the circle maker function. We'll write that custom function, and then we'll be using this Reuleaux triangle function that was downloaded from MATLAB Central. And the Reuleaux triangle function has a sub-function called rotate that it depends on. So we have to download both of those function files. These files are posted up on Canvas along with the solution. Okay, so the solution for the main plotting script file is up there, which has a lot of great comments showing you how to use the advanced plotting functions. And then also a solution for the circle maker function that we'll be going through in this video are posted along with links to the Reuleaux triangle function and the rotate function. So to get this script to work, we need to download the Reuleaux triangle function and the rotate function. Make sure those are saved in either your MATLAB folder or whatever your current folder that you're working in for today is to get all of this to work. Okay, so we're just going to take just a minute. I'm going to set up my screen to jump over to MATLAB, and then we'll start taking a look at those functions and going through today's example. All right, welcome back to MATLAB. So here we are in the MATLAB environment, and what I've got here is just the basic outline of what's going to happen in the main script. All right, so remember the main script is what's calling all of our custom functions and using them, and this is where the plotting is going to take place also. So again, in our example here, we've got the main script that calls the functions, and then we have 3 functions that are being called. We have a circle generator function that's calculating all the data points that are inside of a circle that we can then use to plot in the main script. And then we have the Reuleaux triangle function, which is also calculating points that lie along the Reuleaux triangle, and we'll plot that with the plotting functions in the main script also. And our last function is the rotate function, which is a sub-function of the Reuleaux triangle function. So let's take a look at what's going on here. In the main script, we're just going to start off by clearing our workspace, make sure we get rid of any variables we don't need. right? Once we get into the script, what we want to do is we want to calculate the points that are lying on circles. Okay, so to do that, we need to use a custom function that's calculating the points that lie along these circles. We're going to call that 3 times. What we'll end up doing is we're going to plot 3 circles that overlap with one another, and the region where they overlap is actually the Reuleaux triangle in 2 dimensions. So I've got the basic syntax we'll be using in here, where we define a radius and then we call our circle generator function. Okay, so to understand what the circle generator function is doing, let's jump over and see how we would create that MATLAB file to define that function. So I've got the function already written and ready to go here. And let's talk through what the syntax is and how we're actually defining this function. So first things first, we have to tell MATLAB that we're trying to define a function here. So we use the function keyword. You can see we've got a matching end down at the very end of the script file, or sorry, of the .m file. Okay, and next up we have our outputs defined. Right, so it's always outputs. In this case, we've got 2 sets of outputs. We're going to have a vector of x data points and their corresponding y coordinates that go with them in a separate vector. And that's equal to the function name. All right, you can see the function name matches exactly with the file name of this .m file that's defining the function. That's really important for the .m file. Right, and then just get that to go away there. Then inside of the circle gen arguments in the parentheses here, we have all of our input arguments. Okay, so in our case, we've defined all these variables, and one of the things that's really important to do when we're creating a function is to document what all these variables actually are. So the whole point of a function is that you can reuse the code. So it's entirely possible that you write a useful function and then you come back to it in the future when you use it in a different project. And it's important to document what the function actually does and how to use the function so that you could use it easily in the future again. So down here in the comments, what we've put is we've defined what all of these variables are, so we know how to input those when we call this function. So r in our case is the radius of the circle that we're looking for. We have a minimum and a maximum theta. Okay, so this function is actually generalized, so instead of just drawing a circle, you could draw a circular arc, just part of a circle if you wanted to. Okay, and it tells you if you want to draw a full circle, your theta min should be 0, and then theta max should be 2 pi to have it sweep through the entire circle. And then our last 2 inputs are the center x and y values. So we can move the circle around on the plot, and we don't just have to plot around the origin. All right, and then it tells us also the outputs of what we should expect when this function finishes running, and that's x and y, so the x data points and the y data points that lie along that circle. So we should be able to put the plot, put x and y into the plot function, and we'll draw a circle that way. Okay, and then down after that, we just have the math that actually calculates what those x and y data points are. So remember, the whole point of the function is we give it the input arguments, and then it does its math, and it reports back the output of the function. So there's all of our input arguments going into the function. Down below in the code, we'll manipulate those, and we'll define the x and the y vectors and output those as the function's output value. Okay, so the first thing that we do is we create this theta array, right? So this is the angles that we're sweeping through to calculate the x and the y values. And then the x and the y formulas you hear, these are just pulled straight out of like a calculus textbook of how you would calculate the points that lie along a circle, right? So again, it's just the radius times the cosine of the angle, right? So we're going to have several of those values from our theta array above, and then we have to add the central x value to shift the circle around in the x direction. And then we're doing something very similar in the y for the y data points. It's the radius times the sine to get the y data points, again using theta as the input there. And then we have our offset in the y direction also. Okay, so once you put that code in, right, when we can just save this, we always have to make sure that we save the M file so that MATLAB is using the latest instructions when we call the function. Okay, and then we can go back to our main script, and if that's saved correctly as a function, you can call the function now. So the way we do that is we just type in the function name, the input arguments, and the outputs, and we should be able to run this function and receive back the x and the y data points. All right, so we're actually going to end up calling this function 3 times to create 3 different circles that all overlap a little bit. So what we have to do is we have to change the offset, right? So you can see this circle right here is it's on, this is our y central x offset, right? So it's right on the y-axis, right? But it's shifted up by 1 radius. Okay, so what we need to do is we need to create 2 other circles that fall on the x-axis but shifted off half a radius in the negative x direction, and then another circle that's half a radius in the positive x direction, so that we get those 3 circles overlapping with one another to create the Reuleaux triangle. So we're going to go ahead and we're going to create a second set of x and y values. We're going to call our CircleGen function. All right, and we have to give it the arguments. So our radius is the same. We're still sweeping a full circle, so we're going to go 0 to 2 pi. Okay, and this time our offset, this is going to be the negative circle, so we need to go half a radius to the left, and we want this to fly on the x-axis, so our y offset is going to be 0. Go, and then we're going to do something very similar, except for we're going to shift in the positive x direction on this last line. Okay, so we'll create our next set of x and y coordinates. It's going to be r over 2 this time, and then our y offset is still 0. All right, and we should be able to go ahead and plot these now. So we'll skip over using the Reuleaux triangle function for right now, just to check our work and make sure the CircleGen function is working correctly. So if we just plot x1 and y1, this should just plot the first circle that we've created. All right, and we do get a circle. All right, and my screen's a little bit of a funny size right now since I'm recording, so it looks like an oval, but we can see that the radius is the same in both directions there. There we go. If we make the window square again, then we get a nice round looking circle there. All right, so what you end up doing in this script is we're going to call the plot function multiple times with the hold on. We'll show you the results of that in just a little bit here, but let's talk about how we use this Reuleaux triangle function. All right, so this Reuleaux triangle function, we didn't create this one. This is a function that we were able to download from the MATLAB Central. So MATLAB Central is just like a repository of user-created code where you can go and find people's interesting projects that they've done, they're proud of, they can upload to MATLAB Central, and then anybody can go and download and use them. So if we go into the Reuleaux triangle code that we've downloaded here, you can see that the author has done a really nice job of commenting the code and letting us know where he got his information from and what the variables are in this particular function and how to use it. Okay, so we can see again, this function is actually has 4 outputs, so it has an array of x values, y values, and it has x and y coordinates of the points of the triangle. Okay, so we may not need those values, but they're there and they're calculated if we needed them for some purpose. We're going to call the function using its function name, and it has some input arguments, which we can scroll down in here to find out. So it tells us the x and y are the central point of the Reuleaux triangle, W is going to be the width of that triangle, and then this particular script actually, or particular function, has the ability to rotate the triangle also. So if we wanted to have it at a jaunty angle, we could put in a value for theta and rotate that triangle around. And then also how many points do you want to calculate in there is an input argument. Okay, and it's going to tell us what the outputs are just below there. And you can actually go in, they have all the code that they're using to calculate the triangle. This is checking to make sure it's got the correct number of inputs, right? And then once it's happy with the input that it's received, it is going to go ahead and use math to calculate the different arcs that make up the Reuleaux triangle. Okay, so to use that, we're calling the function just like we did before, and we can just use the standard plot function to go ahead and plot that. Now, I'm going to jump over to the finished example code. So this circleplotter.m, this is posted up on Canvas, so you can go through it also and see the solution of how you can control the plots, because there's a lot of fun options that we can have here to change the way the plot looks, color and control colors, and all sorts of things like that. So the first thing we have here, this is the section where we're plotting the overlapping circles, right? And what we're doing is we're creating a figure. And you notice that when I plotted that figure earlier with just the basic plot command, the window kind of populated up just barely off of my screen, and I had to drag it back down so that you could see it. If you're running into a problem like that, you can actually control where the figure initially opens and the size of the figure by setting the figure's position manually, right? So here we're creating the figure window with the figure command, and if we set a variable f equal to that, we get what we call a handle, right? A handle is just a special variable that allows us to control the properties of something like a figure or a graph axis, right? So what we can do is we can go back in this f variable and use this syntax to change the position of it. Now this section of the code is probably not necessary if you're working on a default desktop, but since I'm recording and I'm at a weird desktop resolution, I ended up having to set that to get my figure to spawn in the correct spot on the screen. Right. From here, you can do all sorts of cool stuff like change the colors of the background in our window. We can set up a subplot. So instead of having two separate plotting windows, we can have one figure window with two graph axes inside of it and plot on both of those individually. That's what we're doing with the subplot function here. And then we go in. Here's our plot command. This is very similar to what we did before. We just used these X and Y coordinates, but now we have some other options out here we can use to change how the graph looks. So in this case, we're setting the color, right? And we're feeding this RGB values, okay? So red, green, and blue get mixed together to make all the different colors that appear on your screen. And Dr. Brodsky, in this case, has gone to the Minds Minds graphics standards. You can pull the exact colors that the school uses on all of its communications, and she's picked those three that go together, so you'll probably recognize them when we run this script here. All right, and we can create labels, and we can change the font size, right? And after that, we can go through and we can plot our Reuleaux triangle also. So on our subplot, we're moving down to the second axis that's inside of our figure window. We can set that up with a separate plot, and then we can plot the Reuleaux triangle that was downloaded with or created with that downloaded function from MATLAB Central. So that's what's happening on this line right here. Okay. Again, we can change things like the thickness of the line and the color of the Reuleaux triangle to make it appear how we want. And then we can even add text to that figure also. So if I run this whole solution, you'll see how all of that's interacting with one another. Here it comes. All right, so you probably recognize these colors from some of the school's communications. Those are official Minds colors that get used. We have the official Minds blue in the Reuleaux triangle, and we're able to add text over the top of it. And you can see that we've created this cool subplot figure with the subplot command where we have one figure above another one, right? So you can go through and you can play with these options in the script. So say we want to change the line thickness of that Reuleaux triangle. We go down to the line where that's being calculated. And my particular script is line 36. It might be slightly different in yours, but I can change the thickness of that line and get it to look nice on the screen. You may want to change different values on there to get it to look nice on your screen. Also, it depends a bit on your screen resolution, how it's going to turn out. You see, when I make it too thick, I start to get these weird little bites out of the corner also. If we make it quite a lot thicker, you'll be able to see that really clearly. There you go. You can see that you can play around with that thickness and change the appearance of the graph that way. All right, so that is how just an overview of what's going on in this function example. For your homework this week, we have just two problems. So one of them, you're creating your own function that's finding the roots of a polynomial, and then we've given you a main script that calls that function. So your goal is to just write the function itself and then just use the code in the assignment to call your function. And it creates a plot based off of the output of your function. So you can try that out, and there's a test case that shows you exactly what you should get if you give it that particular test case where you're finding the roots of a polynomial. And then the last thing that we have is an animated plot activity for you to do. So this is where you're pulling in some data that you're given, and instead of just creating a normal plot, you're going to create a little animation where the data points appear one by one. And that can be fun for different sorts of data analysis exercises. Sometimes it's really effective to show how data progresses over time with an animation. So we'll jump over and we'll give you a little overview of how the animated line function works for that last problem. Okay, so we're back over here to take a look at the animated line function and just give an example of how that works. Okay, so I've set up a basic script file to tackle this example. Again, we're going to clear everything, close all of our windows at the beginning, right? And then the way animated line works is really, really similar to plot. It's just a little bit different how we call it, but we still need the same sort of data. Okay, so we need an X and a Y array, and then we'll plot those XY coordinates on the graph. Okay, so in my case, I'm going to plot a sine wave. So I've set up my X array to go from 0 to 2 pi, and then I'm calculating the sine values based off of that X array. Okay. Next up, I'm creating a figure to plot this. You probably don't need these lines of code in yours. This is more because I'm recording at a weird resolution to make this look okay on YouTube, right? But this is just controlling the figure so that it pops up where you can actually see it on the screen. Right, so I'm controlling that. You can look up the figure position functions in MATLAB if you're curious about how to do that on your own also. All right, so the way animated line works is we create this animation handle, right? So it's a variable that allows us to control the animation, right? And then what we do is in a for loop, we're going to update that variable for the animation with this add points function. And we'll add data points to it one by one, and then we'll see the line be generated as an animation inside of that for loop. Okay, so let's go ahead and just see how this looks. So first of all, let's create our animation handle. I'm going to give this the variable h, and the function is just animated line, like that. And we'll just take the default options to start with, right? So we don't even need any function arguments to use this in its basic form. And now I'm going to create the for loop that's going to be adding the data points to the animated line one by one. Okay, so I'm going to say for equal I equals 1, and then we need to iterate over all the elements in our arrays. So I'll use length x to just iterate over all the elements in x. And I'm going to go ahead right now and add my end to the for loop so that I don't lose track of that later on. So inside of the for loop, what we have to do is add the data points to the animation one by one using this add points function. So we're going to go ahead and call that. It's add points. And then the syntax here is we have to give it that handle to the animated line or the animation. So that was H. And then we tell it which data points we want to add. In our case, we want to add an X data point, and the data point that we are adding is the ith data point. So each for loop iteration, we're adding one X data point and one Y data point to the graph. And we will add the X and the Y coordinates there. And then the last thing we have to do is we have to manually tell MATLAB to update the animation on the screen with the draw now function. Okay, so the reason we have to do that is generally drawing stuff on the screen and creating graphics is slow computationally compared to doing math. And if we had a big complex calculation and we had to have it run quickly or maybe update several times a second, we wouldn't want to try and draw that on the screen every single iteration of that calculation. So you could set up some logic where it would only update the screen every 10 steps in the calculation or something like that to save on computational resources and speed up the code. Okay, so let's go ahead and see what happens when I hit run now. All right, we get our functions popping up. There we go, and we have our sine wave being animated there. All right, so one thing that you could do in this for loop is if you want to control how quickly the animation proceeds, we could add a pause or a delay to the loop and slow it down if we wanted it to run slower. So a good command for that would be pause, right? And we just tell it how many seconds you want to pause between frames. So if I did, say, 1/10 of a second, we'll run that and see how quickly it runs. And you see it runs just a little bit slower now. Okay, so you can control how quickly your animation proceeds there. You can also change the appearance of your animation. That happens up here on the animated line line of code. So if you go in here, what you could do is you could add in options. So the options generally come in as a string, right? So say we want to change the color of the line, we can do that, and then we would give it a code like say R. And that'll should change it to a red line that gets plotted. Okay, and you can also add things like markers on the line. So say we want to have a marker, and then there's all different options of what kind of markers you want to use. Let's try an O and see what that looks like. There we go. We get a line with circles on it forming. And you can, if you just have discrete data points like you do in your homework assignment, you can actually get rid of the line also. So another handy code here is line style, right? So if we do line style, there's an option none. Okay, and this point, we should just get the markers, but with no line connecting them. There you go. All right, so we can make our data points appear that way. So in your homework assignment, you get U.S. Census population data, and then you fit a polynomial curve to that data. So generally the way you'd want to plot that is you'd plot the data points from the census as discrete data points like we did here on this graph with no line connecting them, and then you plot your fit as a line over the top of them, right? That's just a conventional way that you would show that data. And you can animate both of those in sequence. You can show the population data appearing and then show how the model fits that as an animation. So that's a cool trick, and hopefully you'll find that useful in your back pocket of MATLAB sometime. And as always, we are holding office hours this week, so if there's any problems that you run into trying to complete the homework, just let us know. Stop by anytime. We're happy to help you out and help you complete that homework, and we look forward to seeing you. All right, enjoy your snow day, and we will see you next week.